Okay, we are going to look into the various word pre-processing techniques. So the first one is one hot encoding. Now one hot encoding will lead to a lot many features, and so it is rarely used. And then the next technique is back of words. Bag of words uses the count vectorizer class, but it does not capture the inherent semantic meanings. So let us take an example. That is, if I have these four sentences: Alex teaches NLP, Alex provides training, people write comments, Alex write comments. So here if we use the count vectorizer class and I specify binary equal to false, then in that case, here this will be the result. That is, I get a vocabulary, and depending on the vocabulary, depending on the index in the vocabulary, it indicates what words are there. So I can see that there is 0, 2 and 5. So Alex teaches NLP. These three words are included in the first sentence, and so on. So this is the count vectorizer. In case if binary is specified to true, it then captures if the word is present or not, irrespective of how many times does the word appear. So the code here for this is, I have a count vectorizer object and I have another object with binary equal to true. And then I use the fit transform function to on the count vectorizer class and generate a bag of word. Then this is the bag of word and this is the vocabulary for the same. Now the advantages here, disadvantage is it's a very simple technique, but it leads to sparsity. Sparsity as in there are so many zeros that are there. It's not able to handle anything that's out of vocabulary, and ordering is not maintained. So I do not understand what is the relationship of one word with the other. The next is using n-grams. Now n-grams, if these are the words, here in the count vectorizer class itself, I can specify the n-gram range. Now n-gram range can be, if I specify 1 comma 2, it captures two words also. Alex teaches NLP. So let's say if I specify 1 comma 3, then it's going to capture all the three words that are there. So here see, it captured Alex teaches NLP, and also it captured Alex teaches NLP. So here it's capturing whatever are the three words that are together. So provides training, then Alex provides training, Alex provides training. Even those are included. And this is the corresponding bag of word for it. So now we saw bag of word using count vectorizer class, then we saw binary bag of word, then we saw n-grams. Now the problem here is that it is able to capture some semantic meaning, but it leads to large number of dimension. As you can see, with this few vocabulary, I am getting these many dimensions, and also it cannot handle anything that's out of vocabulary. The next technique is TF-IDF. In TF-IDF, we capture the term frequency by total number of times the term appears divided by the total number of documents. And IDF is log of total number of documents dividing by the number of documents containing term T. So let us try to capture this. And TF-IDF score is got by multiplying this TF and IDF. Now, so I make use of TF-IDF vectorizer for this class. I make use of TF-IDF vectorizer class for this. Create an object of the class and then applying it on the text as we saw earlier using the fit transform function. And this is the vocabulary that it gives me, and the final result here is this. So now this is some values that we are getting. What does this each of the value represent? So considering for the term Alex, which is the first word, for considering for the word Alex, we first of all calculate what are the total number of documents. So the total number of times that it appears, in this particular document is 1, and the total number of documents is 3. So I will just add one second. So for Alex, term frequency is equal to 1 by 3, which is equal to 0.33, and IDF inverse document frequency will be 4 by, that is the total number of documents, and Alex appears in 3 of those documents. So IDF is equal to 4 by 3. Internally, how does the calculation happen is, for this 4 by 3, there will be a smoothing. So I have to apply log, that is anyways known, but here there is a smoothing that happens, so that in case even if anything is 0, the final value does not become 0 and it gives me some small value. So here log of 1 plus n by 1 plus df is done. So I get log of 5 by 4 in that case, which is nothing but 1.0969. So here smoothing is applied. TF-IDF values are calculated 0.365. After these values are calculated, these are normalized so that their sum of squares is 1. So I get, after applying these values, I get this. Now here L2 norm is calculated for these values, which is square of all these values. So I get 0.888, and then whatever are the individual values, these are divided by the L2 norm. So here I get 0.365 divided by 0.88, so that gives me 0.411, and the next is it gives me 0.625 nearly. Here I am not calculating the whole as such, so there is some minor change with respect to the decimal points. So here TF is calculated, then IDF is calculated, and then after that smoothing is applied on it so that I do not land up with any 0 values, and then the values are getting normalized also, so that each row basically gets to the sum of squares of values to be 1. And this is how I get the results in TF-IDF. But the problem here is that it is sparse and out of vocabulary values are not handled. Moreover, again it leads to high dimension. So the next that is used is Word2Vec. Now in Word2Vec, we make use of this Gensim class. Wait, I will share the details about this Word2Vec. So we make use of Word2Vec so that we can capture the inherent meaning. Okay, so word embeddings are nothing but the numerical vector representation of words. So instead of representing instead of representing, like let's say till now what we had been doing were another category of techniques. Now what we are going to do is another category. So here we make, instead of representing words as just integer, 1 for apple, 2 for banana, here we are going to use dense vectors, like 100 dimensional vectors, lot of uh, dimensions in the arrays, and that will also help us to capture the inherent meaning. So now we have two major techniques for this, Word2Vec and GloVe. Word2Vec, it's a model which is developed by Google, and here we have um, two architectures for Word2Vec. One is skipgram and the other one is BoW. Skipgram, it will predict the context words from a target word. That is skipgram with something like for example, let's say if I say mat, then it will give me all the words surrounding mat. It's considered like, for example, in when we start typing in WhatsApp also, whenever I start typing 1 or 2 lines, I regret to, and then it shows that, inform that, so it's able to predict the words around it, and that happens with the help of this skipgram concept. Then there is another way, BoW. Now BoW, it has some few words already, and depending upon that it is showing me the next word. So the cat sat on the, it will show me some relevant word that is possible over there. So skipgram will give me few other context words from one target word, but BoW is the opposite of it, where it will predict one target word from few context words. So if we have to see the diagram for BoW and skipgram, for skipgram it will be one word embedding, and then it will calculate many words around it. So this is the diagram for skipgram. But if I see BoW, there will be lot of words that are the context words passed into the model, and then it gives me one target word. I repeat, skipgram, one context word, and it will give me many target words. Whereas here there will be many inputs, but it will give me only one output. And apart from this Word2Vec, we also have GloVe. GloVe is one model which is developed by Stanford, and one second, I will just run this. GloVe is a model which is developed by Stanford, and GloVe is a word which is developed by is a model which is developed by Stanford, and here Word2Vec is based on local context, but GloVe makes use of co-occurrence statistics of word in a large corpus. So GloVe has been developed based on a lot of texts that are already there, and so it builds a matrix of how often words appear together. So first of all, we will see how do we implement Word2Vec using Gensim library, and then we will look around GloVe. So here I install Gensim, get the needed libraries, and here I have the text. Okay, now the text is nothing but the cap seller story. the cap seller story where there is a cap seller who sleeps under the shade of the tree, and the monkey takes the cap, and then the cap seller just the monkey takes all the caps, so the cap seller wants his caps back, and the cap seller throws away his cap, and the monkeys repeat the same, indicating that the monkeys imitate the behavior. That was a small story which we might have already read. So these are the stop words, function to remove the stop words. Now here for this particular story, we apply simple pre-processing, and then once I apply the pre-processing for each of the sentence that is there in the story, these are the various words. Okay, now let us see how the Gensim model has worked. It has applied Word2Vec. I have specified the what is the minimum count, what is the vector size that I am looking at, and it then I specify the story for which I want to build the vocabulary, and then I train the model. So here I have passed the story and what is the model corpus count, epochs that it should run, all that is specified. And then now the queries that I can ask this particular model is, tell me the words which are most similar with cap. And then it shows me help, Sunil, cleverness also. And now I am asking, what are the words that do not match with monkeys? That is, in the story, tell me which is not matching with any other, cap, Sunil or monkeys. And so it tells that monkeys is not matching with cap and Sunil. What is the similarity between cap and Sunil? It gives me 0.14. What is the similarity score between Sunil and monkeys? Minus 0.02. Let me give it some other, cap and cap seller, or maybe cap and tree, or maybe Sunil and tree. So like this, I can understand which of the words here are similar. Now, let's say if I pass Sunil plus the challenge minus the caps. So now I want to see what are the words which are most similar. So there is challenge, Sunil, saw, taking, became, little, repeating his, cleverness too. So now all these words are there. I can also apply, I think here stop words are not removed. Function is included, but stop words are not removed. I can also get the normalized vector for the same. Then whatever are the values for that, so these are the various values after removing the stop words, and I can plot this in a three-dimensional space, and here you can view it. See, let's take this word which is monkeys and started. These two words are far apart from each other. There are three words which are very similar to each other, which are cap, he, mischievous. See, all these words are very similar to each other. Similarly, one, kept. Here is Sunil, back. So this is like viewing the words in a three-dimensional space, so that I can easily see here which are the words which are very close to each other. Now this one is GloVe model. So that was the Word2Vec model, where it helps me to capture the semantic meanings and understand what are the words that are similar to each other. So GloVe is this, and we download the model, and let's say if I have few words, text, the, leader, prime, natural language. I apply the tokenizer on it, and then it shows me that the dictionary is this, and it gives me this is the vector. See, this is the vector that I get for the first word in GloVe. So I apply the model on it, and then I get the vector for the first word. Now again, a similar kind of model, but that was Word2Vec, and this is GloVe. This is demonstrating the part of speech tagging, and see, if I have these few sentences like Sukanya, Rajiv and Naba are my good friends, Sukanya is getting married next year, and so on. So here it is showing me the part of speech, like Sukanya is NNP. We last class we saw about so NNP would basically refer to noun, and JJ is adjective, NNS is noun plural, and this is a proper noun. So here this completely shows me the part of speech tagging, which we will see eventually also.